All right, everyone. So if you check your emails, you saw that Zoom kind of dropped the ball on me and did not record today's earlier class. So that was pretty frustrating. And when I went back into my settings, which I haven't messed with my settings pretty much ever, the record feature was turned off. So something happened, something glitched out with Zoom to have changed that. Again, it's unfortunate, but due to that, I don't want to leave the people that are watching this at night, in theory, or just later, catching it later. I don't want to leave them out to dry. So what I'm going to do is I'm going to do a short, probably 30-minute, that's about what I got. In fact, I'm going to have to check on my dinner that's cooking at some point. I'm going to hear my oven alarm go off and I'm going to have to pause. But so that's life, right? when you have to work from home and teach it again like it never happened. So this is going to go quick. It's going to be a much more abridged version of what I originally talked about. So if you watch both of these, you'll see the differences. Those of you who didn't watch the original, obviously you can't. But the cool thing is when you're watching this on YouTube, if you go down to your settings, which let's say you were watching it like a normal YouTube video, kind of maximized. The settings button is down here in the lower right section. One of the settings is playback speed, and you can set it to like 0.75 or 0.5 or a couple different settings. You can make it go slower. So I'm going to be talking fast and working fast. What you might want to do is adjust the playback speed so that way you can maybe understand me a little better. And also things that I would normally say 4 or 5 times, I'm now only going to say once or twice. So you're probably going to want to rewatch this, maybe watch it at that slower speed, whatever works for you. Hopefully my voice doesn't sound too terrible if you watch it super slowed down or something. But yeah, so let's not dilly-dally any further. Let's get into it. And I'm going to leave all the stuff up here that I wrote, again, just in the interest of time. I'm going to kind of use my highlighter to show you where I am as I go. So 6.1, constant percent change, which I make this point that it's also known as exponential growth. So constant percent change is what leads to what we call exponential growth. And so far what we've seen is linear growth. That's not going to work. So far what we've seen is linear growth. So our lines look like this. This is constant growth. This is the growth never changing. If you're constantly changing every year, or every month, or every day based on a base percentage, like our APR that we've used a few times, what happens is over time, you end up getting, let's say you're talking about money, when you gain interest, that interest then gets stacked into your base value. And then when you get interest on that, it's going to be more because your base value was more, your current balance was more. That's what I mean by base value. So what you end up seeing is growth that looks like this. It starts out kind of slow, but eventually it picks up speed. And then eventually I like to say it explodes, and it's just growing ridiculously fast. And there's a big correlation between this type of growth and your investments when you want to do a retirement plan, like your mutual funds, whether it be through an IRA or 401k or whatever. And I'm talking a lot of language that we'll discuss more at the end of the semester. So linear growth, exponential growth. And this is what we're going to see in some graphs later. Okay, so we saw in the last chapter that if you grow based on a certain value, if you have a growth rate, like 3% in a year, 5% in a year, then you can find the new amount based on the product of the old amount and the growth factor. This 1 plus R is what we call a growth factor. Or 1 minus R, if we're losing, then we call it a decay factor. So growth factor, which is what we see a lot more of in this class, is a 1 plus R. Decay factor is a 1 minus R. So you can always find a new amount if you're just looking over 1 year or 1 month or 1 day, whatever the smallest iteration we're talking about for the problem, based on the problem. The new amount is the old times the growth factor. New amount is the old times the growth or decay factor. Again, 1 minus R of decay. But this is only true over one small interval of time, typically the month, the day, or the year, or whatever it is based on the problem says. So if it says your interest compounds annually, it's once per year. So you have to look at this as a year-by-year basis. If it says that it compounds daily, then you have to do this to get day 5, you need day 4, and then you need day 3 and day 2 and day 1. They just build on each other. So to get day 1000, you have to do 999 calculations before that to get the 9000, the 1000th element. So what we did is we developed a formula that we'd be able to use for compounding rates. So let's say you wanted to know what the amount you have is on that 1000th day. Instead of having to calculate the first 999 of them, you can just use a formula to go from the first to the last. So when we talk about Excel, we usually let that do the iterative process where we let it go through year 1, year 2, year 3, year 4, year 10, year 20, year 30, year 40, all of those in between. Whereas if we were doing this by hand, we wouldn't want to do all those calculations, especially over 48 years or 1,000 days. So we want a formula. So what we did is I'm really sorry for this part having to go quick. I took a long time to discuss this, but on year 0, that's going to be your old or original amount. Now year 0, I'm really going to refer to as the original amount. When we're talking about later years, let's say we're in year 4, I call year 4 the new amount, and then year 3 the old amount. So the new amount at year 3 is the old amount at year 4, or the new amount at year 2 is the old amount at year 3. There's a relationship there that we've discussed previously. So we're just going to use that idea that you can find a new amount based on the product of the old amount and the growth factor. Okay, so year 1, your new amount is the old amount times the growth factor. There's just the equation literally as it says above, red circle. Well, that's the old times 1 plus whatever the rate is. Now, I didn't give you a rate. We're generating the formula. This is kind of a proof, if you will. So there's your 1 plus R. There's your growth factor. But I want to write this as the original instead of the old, because I want all of these based on the original value, not the previous years. So I call this the original times 1 plus R. So then in year 2, the new amount is the old amount, in other words, the ending amount from year 1, this blue underline is this blue underline, times its growth factor. See, each year you get another one of these 1 plus R's. But here's what's interesting. The old amount, when you're in the year 2 segment, is this thing right here, which also has a 1 plus R in it. So there's one of them where I write old, and then there's this other one. So now there's 2 of them, and this happens every year. You get another 1 plus R because you multiply by another growth factor. They keep stacking on each other. But instead of writing 1 plus R times 1 plus R, let's use exponents 1 plus R squared. So then in year 3, it's the same idea. You end up with another of those 1 plus R's. So this green writing was the one from the previous year. All of it, that is. So then there's your extra 1 plus R. So now there's 3 of them. Then by year 4, you stack another one and you get 4 of them. So we use that to develop a formula. Instead of just using a number for the year, we want the variable t. So for year t, the new amount is going to be the original amount times your growth factor, 1 plus R, raised to however many years have gone through. This is called exponential growth because the variable, this t, which is one of the main driving forces, is in an exponent. And my oven's about to beep at me. Give me about 2 minutes. Sorry for having to pause. All right, I'm back, and it just told me something really weird I hadn't seen before. No, I'm scared. I just said something about because I was muted, it wouldn't record, and then I had to hit start recording again. I'm hoping I didn't just lose that first part. Oh boy. Okay, got to continue on. Don't have too much time. So we end up getting this formula once again that the new amount, so for any year, 10 years, 50 years, 90 years later, without having to calculate the rest of the previous years, you just take the original amount, the principal is what we tend to call it, times the growth factor of 1 plus r raised to the t. That's why I said this growth factor concept was so important previously, because we're going to continue to use it for the next several chapters. So here is some very common kind of lettering for several terms. A, we tend to denote as the ending value or the future value, what we were calling the new amount in the previous highlight. P is the principal. This is the starting value, the original value. R is our annual interest rate. Now, if they tell us that we're compounding daily or monthly or whatever, they're always going to give us the annual interest rate. Let me correct that. They are generally going to give us the annual interest rate. T is the time in years. And in that formula, when we're compounding once per year, so we're going to have another formula. We didn't make it that far today, but we will have a variation on this formula when we're not compounding annually, when we're compounding more than once per year. Again, the idea of compounding means you're gaining interest on interest on interest. So that's where we didn't get to. Okay, so let's see some examples using this, and we're not even going to get to using the formula today. All we're really going to do is focus on the iterative side of things using Excel. So I've got some problems, and again, I'm not going to leave them on the screen for a super long amount of time, just because you can pause to write things down and read it yourself. So Bob wants to deposit 10 grand into this is a type of savings account called a CD, a certificate of deposit. It's where your money just, you can't touch it, you can't add to it, you can't withdraw from it. Generally, there's special CDs in existence now, but this is usually you can't move the money until like a year later or 15 months later or 5 years later. So Bob gets a CD and the interest rate's 2%. That's probably about the truth right now. Use this to track the amount in his account as well as his total interest. So two things. We want to know what the balance at the end of each year is, up to 1, 5, 10, and 40 years, as well as how much total interest he's earned. This is what I call free money. Interest, your total interest is free money, because that's money you get for just having your money sit somewhere in a pile and not touching it versus spending it all. So record these values, interest and total, make graphs, scatter chart, etc. So here is just, I kind of identified some information. Your principal is 10,000, the interest rate is 2% or 0.02 is a decimal. If you're doing this by hand, that's 0.02. If you do it in Excel, you can use 2%. And then the time we ultimately want to go to is 1, 5, 10, and 40 years. And remember, when you're looking at a single iteration, no matter what, if it's compounding annually, you're looking at 1 year. If it's compounding daily, you're looking at 1 day. When you're looking at one iteration, you can find the interest from that iteration based on the balance times that APR or the compounding rate, daily rate, monthly rate, whatever is relevant. I shouldn't have APR there technically. I should have periodic rate. But since this is compounding annually, this is true for the problem at least. So it's not wrong. I just should have written it a little more general. That's all. So that's the simple interest formula. Again, it works for when you do 1 year at a time. So to find the interest for the first year, it's 10,000 times 2%, which should be $200. And then to find the new balance, you take your previous balance of 10,000 and you add the interest, which was 200, and you get 10,200. And we're going to keep doing that. When you start the next year, your balance would be 10,200. You multiply that by the 2% to get your interest. Then you add the original 10,200 to get your newest balance. So here's how things look in Excel. That's not the one I want. That was the completed version. This one, I just need to delete some stuff. There's the completed problem. So again, we're going to do this kind of quick. We're going all the way up to year 40, so I've already got those put in. You can type 1 through 40 if you really want to, but I'd prefer to just type years 1, 2, 3, highlight those, and then scroll down using the fill handle or holding the control key down. or just depends on how you do things, whether it's going to repeat the number or whether it will actually increment the numbers. Trial and error is your ticket to winning. So starting amount's 10,000. Your interest, this is the dollar amount. That's the 10,000 times the 200. So we go equals the cell with the current balance times the interest rate of 2%. Now I could have had that written over to the side and then used a fixed cell reference for it. That'd be okay, but let's just keep it simple today. And then the ending amount is the sum of the original starting amount for the year plus the interest you just earned. There we go. Remember, as you're going, ask yourself if these things are making sense. Now, one of those big issues with these finance problems is that you have to link the starting balance of the next year to the ending balance of the previous year. This is super easy to do in Excel. You just go equals, click that cell that you want it to mirror. So now they are forever linked. And I will, in the future, just be able to drag this down as a fill handle because that's a linked amount. This was me just typing 10,000 originally. The interest, I can fill that formula down. The ending amount, I should be able to fill the formula down. Remember, you can double click a cell and look at the blues and the reds and whatever other colors to see if those are the cells you're supposed to be using. And they are. So everything's good. Look at this. Year 2, we made a little more interest because our balance is a little more. The higher the balance, the higher the interest. And this is going to keep getting bigger and bigger and bigger, and that's going to be that snowball effect. So at the first year, we have $10,200 with an interest of $200. That's the first answer, as you'll see as I flip over in a few minutes. Now let's go to year 5. So let's highlight all 3 of these, grab the fill handle, go down to year 5. We have $11,040.81. That's our current balance, which means our interest is the difference of the $11,040 and the $10,000. The difference of those two numbers is $1,040.81. And again, you'll see that on the other page in a few minutes. If we go to 10 years, highlight the cells, grab the fill handle down. Let's go down to year 10. Our total balance is now $12,189.94. Our interest keeps climbing, which means our balance is climbing and climbing and climbing. If we were just making $200 every year, if we just earned simple interest every year, that would suck because we'd be making less money each year. Simple interest, if you try and use it over more than just one iteration, ends up hurting someone if they're saving, and it actually ends up making it more expensive if they're paying things off because you're supposed to be bringing the balance down. Whereas simple interest never changes the balance. Okay, so now let's go to year 40. We've got a ways to drag. 40 is about the number of years people are going to have to work to retire on. If you're 18, 20, 23 right now, you're probably going to go till you're about 67, maybe 70, depending on how that goes in our country. So now we're at $22,000, $22,080.40 specifically, which means there's an interest of $12,080.40. Again, I just subtract the ending balance and the original balance, which is what we put in. Now, we're only putting money in this account once. The third problem we're going to do is where we're going to put money in multiple times, and that's a little more realistic for retiring. We're usually not just putting money away once in our life and then that's it, sit on it for 30 or 40 years. We add to that pile over time. All right, so if you highlight the years, I'm just going to make this chart for everything. I'm going to hit control. I got to scroll up, hit control, highlight the ending amounts, because that's what we're supposed to make a chart against, the year versus the ending amounts. And then we'll go insert, scatter chart, boom. Kind of looks like a line versus that exponential thing I told you about. Honestly, that's what I intended because the interest rate is low. 2% is not a rate that's going to give you that explosion over your 30 or 40 working years that actually enables you to retire. This just gives us 20 grand. I mean, that's cool. But if I could have turned this $10,000 into like $300,000 by somehow getting a higher interest rate, that's what I've got more of an interest in. Sorry for the pun. If you did a linear trend for this, it would be very, very, very close. We've seen an example like that. The R squared ends up being 0.99. Again, I'm rushing this for time. You can find all that stuff by going to add chart element, trend line. I'll do the line itself. And there it is. Then you go to more elements for the R squared. And again, it's close because this really isn't mirroring that exponential model for now. But if you let this go on for another 40 or 50 years, even with that small 2%, it would. So next example. And again, here's all those answers. If you need to pause for the answers, here they are. Okay. And there's just me pointing out that if you had earned simple interest over the 40 years instead of getting your interest compounded every year, that would be $8,000 versus the $12,000. And again, no one does that in real life. That's not how interest accumulation works. All right, second problem. Bob's got 30 grand that he receives from his grandma, whether it was over a good thing or, you know, maybe a sad thing. Sob story there that we're just going to skip. He is going to deposit into a mutual fund. Again, this is basically a type of retirement account. Different mutual funds. There's tens of thousands of these out there, no matter what brokerage you're using, like Fidelity or Robinhood. I'm really blanking on a lot of the rest. Charles Schwab, Acorns. There's some newer ones out there as well, like Acorns. So anyways, he's expecting an average annual return of 8%. Now notice that I'm saying average annual return of 8%. This is an assumption. You can't guarantee this. When you're investing in stocks and mutual funds, a mutual fund is just a bundle of stocks, which makes it safer for long-term investing. Some go up, some go down, but you should, averaging those out, probably earn maybe 5, 10%, maybe 20%, depending on the mutual fund. And 20% is kind of rare, but they exist. But anyways, if you base it off of the S&P 500, which a lot of people do as their basis, we expect to earn an average annual return somewhere between 7 and 10%, depending on how you look at things, how long of a term you look at, and whether you account for inflation or not. So that's what a lot of economists will use as an average return, some number between 7 and 10. And it's not guaranteed. Previous results do not dictate future results, and anything I say having to do with any of this stuff is not financial advice. This is all for just educational discussion purposes. I'm not a financial advisor, but I do like to teach people to be more financially conservative if possible. And today we will do that. I hope, on the third problem at least. So Bob gets 30 grand from grandma. Sad story. Mutual fund, 8% average every year. It's going to go up 20% one year. It's going to go down 50% the next year because it's going to crash because of a virus or the housing market or the tech bubble or whatever. It's happened in our history or will happen in our future because it will happen again. But then you don't panic. You keep buying in, and the next year you gain 98%. And the year after that you gain 30%, and then you lose 25%. All these ups and downs. But the best thing is, at the end, you earn this 8%, and it might not sound like a lot. But let's check it out. So we're going to put this money away for 35 years. Instead of buying some brand new fancy Jeep Wrangler or something and just blowing it all, it would be fun, I'm sure. And if that's what you want to do, that's how you live your life. I will never tell you how to live your life. But we're going for the financially conservative side. We're going to use this to maybe, buy something really big or actually be our retirement plan or part of our retirement plan. So how much will he have? How much was free money, which means how much is interest? You could argue that the whole thing is free money since grandma gave it to him, but with the sad story potential, I wouldn't call that free. That's a cost. So free money, I mean interest. Now we're not going to add to this pile. It's just 30 grand, put it into this mutual fund, sit on it for 30 years and see what happens. All right, so that's in sheet 2. Again, I got a lot of information already up here, so you're going to already see the answers. There they are. All right. So our starting amount's 30 grand. Interest formula, same thing. It's equal to the starting value of the year times the annual interest rate, which we said was 8%. So $2,400 for the first year. Ending amount, that's the sum, equals this guy plus this guy. Boom. More money. Link year 2 to year 1, so equals, and then click that one. All right, they're linked. Now we can drag the interest formula down. By filling it, we can fill the ending amount formula down. Now we can highlight all 3 of these and fill them all the way down to 35 years. And look at this, holy cow, $443,560.33. That is insane, an insane load of money for a deposit of $30,000. Now, maybe this is tax-free, maybe it's not. Maybe you took that $30,000 and you deposited it over 4 or 5 years as an IRA, and then as a Roth IRA, that is, then your interest is tax-free. Maybe you're missing $10,000 or $20,000 from this because of these staggered deposits, but man, that would be a lot of interest tax-free. So how much interest do you actually have? Let's just go equals. Let's take the ending amount and subtract the starting amount at 30 grand. Boom, $413,560.33. That's our interest. That's our free money. We put away 30 grand and we got $413,000. Lot of money. Let me tell you, just by saying, all right, I don't want that Jeep. Let me just put the money away, pretend it never happened, sit on it for 35 years. That's half a retirement. Maybe that is a full retirement if you can live very, very cheap and don't have a ton of medical issues, unfortunately. That's a very expensive retirement issue typically, especially the longer you live. All right, so I'm going to skip showing you all the curve, how I put it all in there. Again, you've seen that stuff before. I don't know why this is in there twice, but it is what it is. Look how these points, this is all of the years versus how much we have at the end of the year. Now we can start seeing that explosion happening. It's no longer a line, and that's why when I did a linear trend line, that sounds funny, but it is a technical term, it doesn't really match it that well anymore. And we saw that with the population model when we looked at it like 40 years versus 200 or 300 years. And the R squared, again, something we're not studying until chapter 8, but the fact that this is 0.1 away from 1, that's like kind of like saying there's about a 10% error in this saying and being a line and correlating, if you will. And we'll discuss correlation again in chapter 8. But again, point of this, if you end up with a lump sum of money, try and put it into a retirement account. And again, this wasn't 2%. 2%, you're not going to have $450,000 at the end of it. You're going to have, I don't know, maybe $70,000, $80,000, and that's not terrible, but I'd rather have $444,000, let me tell you. All right, third, final problem. Again, sorry for the rushing. That slow down button's going to help you. And again, here's the solutions from before. Also, I said, what if the APR was 12%? I didn't write down the answers, unfortunately. Okay, so really quickly. That's not what I wanted. Really quickly, let's just change this to a 12%. That's not going to be an issue. I'm just going to do that and then take the fill handle, and I'm going to re-upload the rest of them. Now look at the ending balance, $1.583 million. Sorry, $1,583,988. That looks wrong, minus B2. No, that is right, that's a 5.3. I saw an extra 8. The interest, that's $1.553 million in interest for free. And again, if you somehow got a 12% mutual fund, if you did your shopping, if you learned a little bit of stuff, this could be possible. Again, I'm not saying it's guaranteed. I'm not saying it's definitely possible. I'm saying it could be possible. There are plenty of people that have outperformed the standard S&P 500. There are plenty of people that have earned 12, 15, maybe even 20% interest every year. They have to research a little bit. They have to learn. They go to YouTube and to Google and to some financial academy, or they just get a financial advisor and hope that he knows what he or she is doing. He or she knows what he or she is doing. Make sure I said that correctly. Anyways, look at this. Now you really, really see that explosion, and you see how bad. Now this is 0.8. Surprisingly, that's not good. Just being that far away from 1 is not good for an R squared. You really want your R squared to be like 0.95 or better if you're talking about a linear trend, because this is not a good approximation. These are terrible approximations. These are negative amounts. That's horrible. Okay, so final problem. Sorry for the detour. Point being, 8% versus 12%. 8% was great. 12% is freaking amazing. So maybe learn a little bit about this, govern your history, and see if you can hit a better number. All right, here we go. My favorite QR problem that I've ever made, and that's not an exaggeration. If you're young, if you're 18, 19, 20, you're going to be, you got another 50 years before you retire, unless you just really know how to squirrel away your funds. So there's 50 years in here from 18 to 68, assuming we're going to do this on both birthdays. Now, Bob likes Starbucks. He spends $3.50 there every day, or maybe $4 at Chick-fil-A, or he's just got this daily habit, literally every day, that maybe you could just go buy some bulk coffee at Food Lion, and then after you divide everything out, how long it lasts over a number of days, maybe it's only 20 cents a day instead of $3.50 a day. Or maybe instead of going to Chick-fil-A every day, you go to Kroger and you buy yourself a bunch of chicken breasts and you split them and you brine them in pickle juice for a day, and then you do whatever their special battering process is, I suppose, and fry them up, and you've got yourself a Chick-fil-A sandwich for maybe $1.50 when everything is said and done. And I don't mean to pick on Starbucks or Chick-fil-A in particular. This could be anything for anybody. It's just about, we tend to have extraneous expenses that, they might make us feel good, but in the long term, they're hurting us financially, because we could live off of something a little cheaper and we could just hold off and then turn that money, we could dump it into one of these mutual funds for a long amount of time, see it explode over these absolutely bonkers factors. And I'm literally going to show you how to become a millionaire on this. So Starbucks cup of coffee, $3.50 a day. So he's going to take this money and save it up for a year. At the end of the year, on that 365th day, he's going to put it into his mutual fund, where he expects to earn 9% return. So he's going to do a little bit better than the average, if you say the average is 7 to 8, but still not some crazy number like 20%. So he's not going to put away $3.50 a day. That would make the problem a little more complicated. He's going to take that $3.50 and put it in a box every single day, or just not spend it every single day. End of the year, that's like $1,277.50. So he's going to then take that $12,750, put it into the account, and then it's going to sit in there for a year, and then it will accrue 9% interest over a year, and then he's going to dump another $12,750 into the account, and he's going to keep doing that. So he's not just putting money away once, he's going to put money away for 50 times. So how much will Bob have to retire on? How much was interest or free money? Make a scatter chart. So at the end of each year, $12,750 is going to be his deposit. So you're going to notice that it's not just 4 columns, it's not just year, starting amount, interest, and ending amount, because now we're adding to it. We need 2 extra columns. We need a column for the original balance. We need a column for how much we add into it, how much we have before we calculate the interest, then the interest calculation, and then the new ending balance when we add the interest to the original balance and the money added pile. So let's just clear all of this. Again, you can see a lot of the numbers. And in fact, let me move some of this stuff. Again, these are just summaries of answers for later. All right, so we're going for 50 years. So, all right, I only go to 30 because that's part of the later question. I said, what if you miss 10 years? What if you miss 20 years? Let me highlight the 29 and the 30. That's going to tell, and then I grab the fill handle. That tells Excel to increment. I got to go to the 51st row because that'll get me to year 50, because the first row are titles. Starting amount. We start with nothing. We're starting with nothing. And I don't know why I typed the $sign. I want to do 0 and make sure it's formatted as currency. There we go. So nothing. We start with nothing. But then we add that $12,750. Pre-interest balance. That's the sum of what we originally had and what we added in. We literally added. So equals what we originally had for the year plus what we added for the year. And we're going to add the same amount every year. We're not going to inflate this amount, which makes it even more interesting, as I'll discuss. Interest, this is the product of your pre-interest balance times your interest rate, which we said was 9%. The ending balance is the sum of the pre-interest balance plus the interest. So at the end of year 1, we got a little more. Now, there's a little squirreliness in this calculation because technically if we put the money in on the 365th day, we would have never earned interest on it. So what I'd like to say, really the association of this problem is we have a year 0. During year 0, we build up our army of dollars. We build up our first $12,750. That way for year 1, we deposit that in. So year 0, there's no interest because we put the money in at the very end. Then for year 1, we add in that $12,750 at the very beginning to the original pile of the 0, which gives us our pre-interest balance, interest, and ending balance. Okay, so we got a link equals the new balance to the old balance of the last row. Then we can drag down the money added formula, but look what happens. It does not change it if I only grab this column. Let me undo that though. If I highlight all 4 of these and fill it down, it adds 1 to it. So that's some of the weirdness of Excel that you just have to try and learn and pay attention to what's happening. So I'm just going to do these column by column. So the 12, 7, 750, let me add that for all the 50 years. Okay, that looks good. Let me bring that starting balance formula down, the 50 years. And it's all zeros after that because none of these are, the rest of these are fine. You could do them one at a time, but I know I can do them all 3 at once. Again, I'm shortcutting some techniques and stuff. Holy cow, $1.1 million. $1.1 million. What did you do? You gave up a Starbucks cup of coffee a day, or again, just something small in your life. Maybe instead of having a $10 lunch every single day, maybe it's a Subway or what's a fancier one, Firehouse, where they're a little more expensive. Instead of doing that with a drink and some chips, you just get some deli meat and some bread, maybe even some good bread from the grocery store. You make yourself some sandwiches at home and you save yourself $6, maybe even $7 a day on your lunch. And then you put it away for 50 years. Now, this requires a lot of time. This only works on 50 years where you end up being a millionaire on a Starbucks cup of coffee. So if you're like me and in your mid-30s and maybe didn't start this when you were 18 because nobody told you to do it, I really wish I had those people in my life, and I hope that I'm going to teach you something on this, because if you wait to start, let's say you wait 10 years, and oh, by the way, here's your amount deposited. We only put $64,000 away. We could have put this into a Roth IRA, which means it grows tax-free. Our interest is the difference of, and now this 63,000 was all the sum of these 12, 7, 750s, all 50 of them, which means we got over $1 million in interest tax-free. $1 million in interest, tax-free. Now we buy our yacht. Now we have a nice quiet home in the mountains. We relax. We go and take 20 vacations, whatever it is. Now you can't siphon that away instantly. You've got to use it over time, but that is a retirement on a Starbucks cup of coffee a day. So, all right, you're 28. You only got 40 years to go. What you do is you just cut the last 10 years of this off. So when you do that, and you can see that information over here, that's the waiting 20 years. I thought I had an analysis for wait. Yep, no, here it is. It is in there, all there, okay. So by waiting 10 years, now that Starbucks cup of coffee only gets us 430,000. And I had to play around with the numbers, and I'm not gonna keep doing that. But if you wait 10 years, instead of being able to deposit $350 a day, what it boils down to is you have to put away 8.22 per day, which is a total yearly deposit of $3,000. So you go from $1,200, $1,300 to $3,000. That means your daily deposit is 2.35 times as much as it used to be. That's by waiting 10 years. So again, just doing the original deposit, you're not even halfway there. You're like a third of the way there, just a little more than that, honestly. So you have to up your daily deposit. Waiting 10 years means you have to up your daily deposit. All right, what if you wait 20 years? You're 38 and you finally start this whole process. Well, the original Starbucks cup of coffee now only gets you 200 grand, which honestly is not retirement bucks unless you've got other funds elsewhere, 401ks, pensions, your whatnot. So by skipping 20 years, what it turns out to get that same $1.1 million, you have to put $20.55 away every day for $365, and that's about $7,500 a year. Now, right now, a Roth IRA Contributions Max is $6 grand per year, so you would not actually get all your interest tax-free. There would be some that you'd have to pay taxes on. Now, that's not the end of the world. The worst part of this is, though, is by waiting 20 years, you've gone from $3.50 a day deposit to $20.55 a day, which is 2.5 times large as the 10-year minus goal, which is 5.88 or 6 times as much as the original deposit every day. Time is on your side if you're young and you take this serious. Now, if you have high interest loans, if you have any student loans over 9%, car loans over 9%, for some reason a mortgage over 9%, refinance it, please, if that's the case, because I don't know where you're living. with a 9% rate, unless you've got terrible credit, and that could be the case. Credit card debt. You get rid of all of those things before you start putting money into retirement, because credit cards are 20%, and the basic idea is you put your money where the higher interest rate is. So if you've got 20% credit card debt, you got to pay those down before you start putting away to your 9% retirement funds. Those credit card debts have got to get gone. Now, if you're just going to decide to live your whole life with credit card debt, then you need to handle both at the same time, but that's not the wise thing to do. So, all right, next class, I've got to go now. Next class, we're going to continue where we left off. We're going to take that first example. We're going to use that new amount equals old amount times the growth factor raised to the t to compare the numbers that we got from year 1, 5, 10, and 40. Oh, and by the way, here was the chart for it. Look at that explosion. Oh no, it's missing some of them. I got to undo some things. There we go. Look at that explosion. Here, the linear growth is down here, but by like year 25, all of a sudden your money just starts taking off. The fact that you're adding that 1277.50 really doesn't even matter anymore at this point, because your balance is so massive in comparison to that 1277.50 that the interest is what's causing it to explode, not your addition. But your additions, especially in the beginning, are what help it start that fuel. All right. So we're going to call it there. I am crossing my fingers and praying to everybody that this is going to record and that everything's fine, because I'm not doing this a third time. Again, pause will be your best friend. The slowdown feature will be your best friend. I hope this is helpful. I can't apologize enough for this technological fail, but take it easy. I'll be recording tomorrow's class, Thursday's class tomorrow, and this will be uploaded soon, assuming it exists. All right, bye.